Good morning. Today we study about the Einstein relation between semiconductors. Okay. Now, this relation gives the Einstein relation means of semiconductor gives the relation between drift current and diffusion current. It gives the relations of coefficient of diffusion and the mobility of charge gas. That is nothing but Einstein relation for semiconductor. We consider a semiconductor at a room temperature, and it is distributed with a different charge carrier. Now, here we consider at a thermal equilibrium. At thermal equilibrium, both currents, diffusion and drift current, both are equal. So, we know that the current density for drift current is given as Jn is equal to the drift current Jn for n-type semiconductor is equivalent to Jn diffusion. Hence, drift current is equal to diffusion current at thermal equilibrium. Here, the Jn is nothing but Ne, the concentration of electrons into mu n into where mu n is known as the mobility of n-type semiconductor is the applied electric field, which is equal to dN into E. dN is nothing but the coefficient of diffusion coefficient, dN by dx, where dN by dx is nothing but the concentration gradient. We know that the force, the Lorentz force, is also known as the alphastatic force, is nothing but the charge into electric field. So it is nothing but N E into capital. So here the term Ne into E is nothing but force. So the force is equal to Ne into E is nothing but, you can consider the mu n is taken in this left hand side, then it is equivalent to dN by mu n into E dN by dx. That is the equation number 2. Okay, where dN is the diffusion coefficient of n-type semiconductor, mu n is the mobility of n-type semiconductor. This is the force due to the equilibrium position. So here what happens, the thermal excitation will be takes place. So here there will be a thermal pressure will be produced due to the excess of charge carrier. So the thermal pressure is nothing but thermal pressure of the force is equal to Kt, where K is the Boltzmann constant, is the absolute temperature, into dN by dx. That's the equation number 3. So at thermal equilibrium, we equate both equation 2 and equation 3. then we get dn by mu n is equal to, dn by mu n into charge into dn by dx. The concentration gradient dn by dx is equal to kt into dn by dx. Okay, now cancel this. So finally we get dn by mu n is equal to kt by g. This is for n-type semiconductor. Similarly, for p-type semiconductor, dp by mu p is equal to kt by e. The equation number 5. Now, equating 3 and 4, we get dn by mu n is equal to dp by mu p. So finally, it implies dn by dp is equal to mu n by mu p. This expression is known as the Einstein relation for semiconductors. That is mu n which gives the relation between both drift current and diffusion current. Means the coefficient dn and dp are the coefficients of diffusion current for n-type and p-type respectively, where mu n and mu p are the mobility of charge carrier for n-type and p-type semiconductor respectively. Okay, thanks.